Good evening, everyone. Welcome to the session. Let's wait for a few minutes till 7:05, then we can start. Right, everyone, let's get started. Let me introduce myself. My name is Buruj. I'm a fourth year PhD student at IIT Delhi. I research graph machine learning. This is week 6 of data analytics with Python. These are our practice sessions, and the goal of these sessions is to practice whatever you have studied theoretically to apply that in code so that you can gain the confidence to do it yourself. The way we structure these sessions is that we take up a practice problem for, and then we take, let's say, 7 to 10 minutes to solve that. I give you that time, following which I help you through the solution. After that, we discuss if there are any doubts, and then we move ahead. There, let me share the screen. Whenever we discuss any of these coding questions, we upload the notebook to this GitHub repository, so you don't have to take any screenshot, etc. You can find the code here. For example, this is the code for the previous week. We have these. Similarly, these sessions are also recorded, and you can find the recordings at this YouTube channel. And I'll share the link after the session. Okay. So can you please confirm if the font, etc., is okay so that we can start? Can you please type in the chat? Okay. Thank you. So in that case, this week we are mainly covering, I believe, linear regression because ANOVA was covered last week. So let me paste this code snippet here. So the idea here is that we have synthetically generated some linear data and we have added some random noise. Our ground truth is that the linear model is 2.5 times x. X is our independent variable plus 10. 10 is our coefficient. To that, we have added some Gaussian noise. np.random.random n. It essentially adds, if you would hover your mouse over it, it says it takes noise from the standard normal distribution, and then we have scaled it a bit. Okay. So if, for example, you were to reduce this, you will get less noise, but we've kept it like that. Okay. So given this data, please train a stat model's ordinary least squares to find out the coefficient as well as the statistical significant stuff. OLS using stats models. You can take 5 minutes to maybe do it. This is pretty easy. Okay, let me give you the code generation. Yeah. All right, let's get started. So the first thing is that you should import the ordinary least squares from stats models. We can check the documentation. It looks something like this. It takes two main variables, your endogenous and your exogenous variables. Your endogenous variable is essentially your dependent variable. That is the thing you are predicting, your y. Your exogenous variable is your x. That is the independent variable. Okay. Um, Sanjita, I'll come back to you in a minute, okay? Once we go through this. So we have these two things. So let's try it with that and see what we get. We can say our model, in our case, let's say model one is equal to ordinary least squares. Our endogenous, that is the thing that we are predicting, is y, and our exogenous, that is the thing that is independent, is our x. All right. And we have this model. Then we can call fit on the same model, or you can do it in the same line as well. You can do something like this. You fit the model, and then we can print it summary after it's fit. So model.1 dot summary, and we see what we get. So you would notice that we get this x1. So the way stats model does it is says that y is equal to x0 plus x1 times your exogenous variable. You can write like this: xor is equal to endogenous is equal to this thing. So x0 would be your constant term, x1 would be your slope essentially. You would notice that we didn't get a constant term, we only got x1. Even in that x1, we are not matching the ground truth. X1 should be 2.5. We are at 4.185. So what happened? So the thing is, our x, if we print that, it is a single variable. It does not have a constant term attached to it. If you go to the documentation as well, there is an additional argument which says has constant. Has constant essentially says, do you have an additional term of essentially unity that I can use to find your coefficient? To do that, you have to manually add a column of ones to your data x. Okay, there are two ways to do it. You can either use numpy to prepend a column of ones, and the other option is that you use stat models helper function, which looks something like this. You have this function called add constant. You can say, let's say x prime or x bar is equal to add constant to x. And if you print this now, you would notice that now we have two columns essentially. For every data point, you have a constant one and you have this. If you train your model the same thing using this, we say again, endogenous is y, exogenous is x, and has constant is equal to true. And then we print the summary, mm, x bar. You would notice that now we are getting x1 as well as the constant, and we are pretty close. So it's 2.4685. Our original is 2.5, so almost the same. Similarly, the coefficient is 11.11, and we had actually set it to 10. So we're pretty close. We can also visualize the same thing. We can say figure comma x is equal to. So before we plot this, does anyone have any questions with this part? You can maybe unmute if anyone has a question, any doubt. All right. So we can plot our regression line to see what it looks like. We can say figure comma is equal to plt dot subplots. This essentially creates your figure and an artist. You ask your artist to create a scatter plot between your x and your y. You can say that I want a transparency of 50%. And if you want, you can label this thing as your data. Okay. And we can say ax dot set my x label should be x, my y label should be y, and we can also set a title saying regression line, and we say plt.show. Okay, so this is again our old line. Now we need to draw our regression line. Okay, so to draw a regression line, we essentially need the x values going from this range 0 to 10. That is whatever our data range is. So to do that, we can say that our x min is equal to this thing. Our x max is equal to x dot max. And we would like, suppose, 100 points between these 2 points. So we can say that x underscore line is equal to np dot linear space. So what np dot linear space does is it picks up, for example, if you provided this a minima and a maxima, you have to tell how many points to pick. Suppose we ask it to pick 100 points, it will pick 100 points at an equal distance from each other. So for example, if I ask it to pick, let's say 10 points between 0 to 10, it will pick 1, 2, 3, 4, 5 at equal distance. Similarly, if you ask 20, so 0 0.5, 1, 1.5, 2, and so on. So once we have, suppose this X line, we have picked up 100 points. What do we do with that? We would like to say y underscore line is equal to beta 0 plus, so essentially our beta 0 and beta 1 in this case are beta 0 comma beta 1 is equal to model underscore 1 dot params. We can print these. I think this is without braces. Yep. So we have beta 0 and beta 1. We can straight away say that it is just beta 0 plus beta 1 times x underscore line. This is my y output. Now I can just plot this thing. I can say ax dot plot. My x-axis should be x line, y-axis should be y line. We can use a different color. We can say make it red, and we can provide a label saying this is an ordinary least square regression line. And since now we have labels, we can also do a legend. Okay, any questions with this? Okay, so moving on, in case we don't have any questions. We also notice that along with these beta 0 and beta 1, we get a lot of extra information here, which is essentially your statistical significance. What is your fitness, goodness of faith, essentially your R square? What is the F stat? What is your P value for that thing? Similarly, you also get the, where is that? Yeah, the T statistic, the P value for that statistic, and your 95 percentile, 95% confidence interval. Okay, so we notice that our T statistic for X1 essentially is this much, and its P value is 0, which is less than 0.05, significantly less than 0.05. So you can safely reject the null hypothesis that it is that your X1, that is your slope, is not 0. There is definitely some linear correlation between the data. Okay, and Similarly, you have your 95% confidence, this thing, you have it between 2.1 and this thing. So it is not zero. Clearly, zero is outside this range. Okay. So can you identify these things manually and compare whether they match? It's summary. So you can refer to the lectures. You have essentially have to do it sequentially. You will start out by finding out beta 0 and beta 1 manually. First, you will identify these two things manually. Once you have these, then you will go about this thing. You will first have to identify the t statistic. From the t statistic, you will get the p value and the confidence interval. These are your t statistics for the x1 itself. Then for the model as a whole, you can identify this r square, which is the goodness of fit. And from the r square, you will get the f stat and the corresponding p value. And based on that, we can see whether they match or not. And then we can move forward. Okay. So you can take 10 minutes maybe. This is a bit harder than that. So we'll see. So your steps would be manually compute the coefficients of OLS, find the t statistic for x1, which is essentially your slope. Then you will find the p-value for, by the way, your x slope is also your beta 1 in our case, just for this. So we can find the p-value for beta 1. Then you will find the confidence interval for beta 1. So this part up to this point is for your x1. Then for the model as a whole, you can find the r squared for the model, followed by the f stat. Okay, so maybe we can also do it in two parts. Maybe you can try this thing first, and then we can go for this part. Okay, let's compute the first part. To do this manually, let's follow some convention first. For example, if we need something like x minus x mean, like something like this, we will write it like this, x underscore x bar, okay? Because x mean is usually shown by x bar, and whenever we use it underscore, it will essentially mean x minus this. This will be the convention that we follow, okay? So we can say that x minus x bar is equal to, you could also write the full thing, it's just, I mean, longer to, x by x bar is equal to our x value flattened. So by the way, we are flattened because our x thing like this, it is a 2D array. It's n cross 1. We would rather have a flattened array, which is a 1D array, which looks something like this. If you print the shape, it's just 100. It's a single list. Otherwise, if you don't flatten it, it's a 2D array like this, 100 cross 1. Okay, that's why we are flattening. So we have x flatten minus x dot mean. This is essentially your linear function, and you are taking this. So x minus x bar is this array. Similarly, y minus y bar, that is y minus y mean, is equal to y minus y dot mean is equal to this thing. We have these two values. Based on this, if we would like to compute our beta 1 and beta 0, we know that we can do this like this. Beta 1 is equal to a summation of x minus x bar multiplied by y minus y bar divided by the sum of x minus x bar squared. This is our beta 1. Our beta 0 is just y dot mean minus beta 1 times x dot mean, and then we can print our beta 0 plus, I can say, OLS is equal to beta 0 plus beta 1 times x, or we can just write x. So 11 point this 2.4685 times x. We got the same thing here, I believe. 11 point this 2.4685 this. Okay, so we're getting the same thing. So this was the manual computation of the coefficients. How do we get the t statistics after this? Okay, so to do that, let's compress this part a bit. Now we can move on to the test statistic. Here we would first need the predictions. So our y predictions are essentially our beta 0 plus beta 1 times x dot pattern. As we said earlier, this gives us the predictions, which are essentially this thing, like your predictions for each individual point along this line. These are your y predictions. Then you will compute these terms, your sum of squared terms, sum of squared, sum of squares for regression. You will compute SSE, which is your sum of squared errors. Then you would compute the total sum of squares. You will need a degree of freedom. And then finally, you will compute that S thing, which is also called S2 in that case, which is your unbiased estimator of variance. Okay, so let's go with this step by step. What is SSR? SSR is your sum of squares for the regression thing. So it is simple to compute. We have y minus y pred, sorry, only y pred minus y dot mean. We take this difference, we have to square this, and then we have to sum this. NP dot sum. Okay, so SSR is your y prediction minus your y mean. This is your this thing. Now you have to go for errors. Error is just y minus y prediction. So NP dot sum y minus y prediction squared. Okay, so we have two things. SST is just the sum of these two, so we can say SSR plus SSE is our total sum of square. Your degree of freedom in this case is the length of x minus 2. Essentially, it would be minus 1. But if you would remember, since we only have one independent variable, it will is that k in this case is just 1. So it is n minus 1 minus 1. So we can also write it here. So data number of data points minus 1 minus number of um, essentially endogenous variables. I believe it's endogenous, right? Yeah. So we have this. Finally, we can compute our S. Our S is essentially the NP dot square root of SSE divided by your degree of freedom. Or you can also do it like this. You can write NP like raised to 0.5. It's up to you. So we have our S. Using this S, we can compute the test statistics. From S, we can calculate the SE for beta 1, the standard error for our beta 1 term, which will be S divided by the square root of x minus x bar squared. And our t stat is beta 1 divided by standard error of beta 1. And now we can print this. So it's pretty dry stuff. You essentially have to follow the same process. That is, you what is the final thing that you need, and then you retract. That is, for this thing I need S, for S I need SSE, for SSE I need Y and Y prediction. So that's how you do it. So we can say our T statistic for beta 1 is equal to T start beta 1 14.144 T start 14.144. We're getting the same thing. Next is the p-value for this thing. So if you would remember, the null hypothesis in this case is that the beta 1 is 0. That's the null hypothesis. And the alternate hypothesis is that it is not equal to 0. When we say that it is not equal to 0, we have to take a two-tailed t-test. We have to check the right-hand side for greater than and the left-hand side for less than. So to do that, we can say that our p-value for beta 1 is equal to, we can take the right-hand side first, the higher tail, t dot. So t essentially we have already imported it here. From scipy.stats, we have imported the t distribution. So what are we doing now? We take the t distribution CDF and we take the absolute value of our t statistic, this thing, and we pass the degree of freedom. Degree of freedom is equal to this, and we have to double this value because this is a two-sided test. I think everybody is okay. Wow, everything's closed, right? Yep. So we have our p-value. We can print this again. We can say p-value for beta 1 is equal to p-value beta 1, again 0.3f. It is essentially equal to 0. To format this a bit better so that it looks cleaner, we can maybe align this part. We can say this part can remain like this. This part can go separate, and for this thing, we can align it like this. Why is it not allowing it to? Maybe we should add a slide to print this first. Similarly, we can do the same thing here. We can say you have your own f string, and we can align this f string to occupy 35 spaces. And in those 35 spaces, I would like you to be right aligned. So something like this. We can reduce this as well. Okay, something like this. But for later, I mean, I think 35 would be a better option because we have more text about. Now, going to the confidence interval for the same thing, how do we compute the confidence interval? We have an alpha of 0.05 because we need a 95% confidence interval. For the confidence interval, we would need the T critical value, which would be T dot ppf, which is the reverse of your CDF. You will supply the higher tail value, 1 minus alpha by 2, because we are taking a two-tailed test, and again you will supply the degree of freedom to be this much. Your CI lower is just your beta 1 minus T critical times the standard error of beta 1. Your CI upper would be the sum of the same thing, and then we can print once again. You can say the 95% confidence interval for beta 1, and it was equal to CI lower, comma, CI upper, 0.3f, 0.3f, 2.122, 2.815, 2.122, 2.815. We match. And again, to align this, we can make the first part occupy 35 spaces by doing this. This makes it take 35 spaces. Then we can say within those 35 spaces, please align it to the right side. So when we do this, it does something like this. T star, p value, 95% confidence interval. Okay. Any questions in this, in the code? Okay, moving on. So now that we have all of these, now we need the R square, which is the goodness of it, as well as the F stat for the full model. So how do you do that? The R square is equal to just your sum of square regression divided by your total sum of squared, and then again you print. You can say R squared for the model was R squared, take 3 decimal places, we have this thing, we repeat like this. Okay, and then the F stat. For the F stat, we would get the F stat like this. It is essentially your MSR divided by the MSE. Now, what are these MSR and MSE? These are two extra terms. MSR is equal to your SSR divided by 1 in this case. So what's the 1? 1 here is the, again, the number of independent variables that you have. In this case, we only have 1. So we can also write it dividing by the number of predictors. Your MSE is your SSE divided by degree of freedom, which is essentially your standard error. Degree of freedom you have already computed. So we can do this. We have MSR, we have MSE, so we get our F stat. For this F stat, we can also get our value for the F stat. This would be 1 minus T dot CDF, our F statistic, comma, DF is equal to DUF. And I think that should be it. So we have our F stat, and we can say print F stat for the overall model. Yeah. So like that, we have essentially matched everything. So this is on the practice side. Now let me share something with you that may prove helpful down the line. Okay. So before that, let's maybe first plot this thing again. And rather than writing the whole thing again, we can turn this thing into a function. We can say define plot regression line. We can do this. What do we need? We need x, we need y, and we need the coefficients. We can need beta 0 and beta 1, and we have our function. We can utilize this in future. We can say we have x, we have y, we have beta 0 as well as beta 1. Can place this plot regression line. Yeah, so now we can reuse this. So we can say plot regression line. Our x is same, our y is same, our beta 0 and beta 1, we have calculated them here, beta 1, beta 0. We can again print these. Same thing. Okay. Now consider the scenario where a good fit of your data may not always imply that the relationship is linear between the data. So good fit does not imply correct model. Let me give you an example of this. You can close this part. Let's create a data set which is not exactly linear. So you would notice that this data set does increase as x increases. So as x increases, your y value increases, but it is not exactly a linear equation like that is you can do mx plus c. You can notice that there is actually some oscillation between this data set and some non-linearity, because the ground truth is that it is 5 times x, which gives it the increasing function, but there is also a sinusoidal component to it. Okay, so suppose you did not know the ground truth. Okay, we did not plot this particular line. You have this. Okay, and you assume that this is linear and you go ahead with this and see, let's see what ordinary square would give me. Okay, so we would do as we just did. We will add a constant, which would be add a constant to x, and then we'll say our model 3 is OLS. Our endogenous value is again y, our exogenous value is x prime, and we have a constant term, and we can call fit on this, and we can say print model dot summary, model underscore 3 dot summary. So you would notice that our f stat is essentially, I mean, our p value of the f stat is essentially 0, and our goodness of it is also quite good, so 0.8. So this summary tells us that we can safely reject the null hypothesis, and then rejecting the null hypothesis says that your x1 essentially is not 0. There is some slope to your data, there is some relationship between your data, but you should not read it to mean that there is a linear relationship between my data. That is, this thing x1 times my x value plus my constant, this is the correct model. This need not be the correct model. If we are to, let's say, print it, if we were to do it like this, um, beta 0 comma beta 1 is equal to model underscore 3 dot params, and then we can do plot regression line. We will have x, we will have y, we have beta 0, beta 1, So you notice something like this. It will fit the data to the best of its ability. So in this case, it is minimizing this thing. Here, it is minimizing this thing, but this is not the correct model, even though this is the best possible linear model. Okay. So when you reject your null hypothesis, this does not mean that you have a linear relationship. So suppose you have a one-dimensional data, you can obviously visualize it. You can see whether it is actually linear or not and go ahead. But in real life, you may not only have a single feature. So even if you go like 3 or 4 features, you can no longer visualize your data set. In that case, you can still fit this OLS model, but you won't have this visualization to aid yourself. You will only get this thing. You will get that, okay, your X value is this much, you have a pretty good P value, you have a pretty good goodness of fit, do what you will with that. So in that case, you reject the null hypothesis, but you're not sure still that is my linear model the best model? So that is one thing to take away with that. The second thing is the opposite. Suppose you fail to reject the null hypothesis. Let us so so our null hypothesis essentially says that there is no relationship between the x value and the y value. They are essentially independent of each other. There is no correlation. Suppose your data set looks something like this. Okay. Does anyone have a question? Degree of freedom is n minus one, but you wrote why use length of x? Um, we don't write length of x minus k minus one. We wrote length of x minus k minus one. So this length of x essentially is your n that you're saying, like n minus one. This k in this case is the number of independent parameters of your model, and that one comes from the that starts thing here. So that those things are not inside the length function. Yeah. So moving ahead, our null hypothesis essentially says that our x1 is equal to 0. Suppose we have a data in which we fail to reject the null hypothesis. Okay. Always notice that we don't say accept the null hypothesis. Whenever we do a statistical test, we either reject the null hypothesis, or we say fail to accept or fail to reject the null hypothesis. So why do we use this term, fail to reject null hypothesis? So suppose we have a data set that looks something like this. Mm. So you would notice that this is clearly nonlinear. It is a parabolic shaped data set. Suppose we were to fit a linear model on this, let's see what we get. Okay. We can say again that our x is equal to, we add a constant to this thing, and we'll say model 4 is equal to ordinary square. Our endogenous is y, my exogenous is x this thing. We have a constant term, and I'd like to fit the model. Please print the model summary. So in this case, notice that your p-value here is 0.185, right? In this case as well, 0.185, which is greater than 0.05. So you fail to reject the null hypothesis. If we were, suppose I did not give you this thing, the plot, you only saw this much. You would essentially say that, okay, there is no linear relationship between my x value and my y value. They are independent essentially. But is that so? Are your x and y values independent? Clearly not, right? Therefore, whenever you have your data and you fail to reject the null hypothesis, it may still mean that your data just isn't linear. Okay. If we were to suppose plot this, we can say beta 0, comma beta 1 are my model 4 parameters, and we can say plot regression line. We have x, we have y, beta 0, beta 1. You see something like this. It is giving you essentially a flat line because it's trying to compensate this part, and this part, and there are roughly equal number of points below the line and above the line. So to minimize the ordinary least square, that is the residuals, this is the best fit that it can essentially get. And this essentially gives you this slope, almost a zero slope and a very small p-value. But that does not mean that you have, let's say, a poor value. In fact, you can manage this pretty easily. If instead of using x, if you have a hunch that I might actually have a nonlinear function, you can square your value of x. Okay, suppose we do something like this. We can say x is equal to this thing, and then we print this. Let's see whether we can get the values in this case. No. So essentially we need an extra column in that case. Yeah. So the idea is that you have your x like this, right? So you need an extra column which will contain the square terms. Okay. So maybe we can do np dot stack. We have x, we have x square. Maybe this will work. Does it work? I think it worked. Two divided by one. 100 by 2. Yeah, this is good. So suppose we try this. We have XS and we have an additional listing. Now, if we try this, do we get an extra column? No, it does not fit it. A 1D, oh, it expects a 1D thing. Yeah, so that would take a different overless, linear model. So suppose you do it using the scalar model. In that case, you will receive an extra term here. So you will get a constant term, you will get x1, and you will get essentially x2. Scalar linear regression. Hmm. Now this should work. So in this case, you would notice that we have three terms. You have a constant term, you have one for x, and you have one for the x squared term. So if you provide your linear regression model with an extra term, which is the square term, it can still do something else. This is called polynomial regression. So this is not covered in your course. This is just in case you need it in future. Yeah. Any questions with regard to this? Okay, if we have no questions, we can end the session. To reiterate, you will find the code at this GitHub repo. Let me paste the link and you will find the recording here. So as far as Tanu's question, are the coding questions coming in the final exam? I don't think so. I don't think because he doesn't cover it, the professor doesn't cover it like this, so probably not. If you want, you can still ask them. I don't think, no. All right, so I'll end the session. Thank you for your time. See you all next week.